Swayam Prabha. Digital India. Educated India.
Okay, so coming back to this expression for Z0. Z0, by the way, is called characteristic equation. Okay. So Z0 is given by L upon C. Okay, so this is the relation for Z0. Now, as we shall see, the two most important parameters for any transmission line are this Z0 and this gamma, or for a lossless case, gamma, which has a real part. The gamma is complex and can be resolved into a real part alpha and an imaginary part beta. So for a lossless case, we see that gamma is purely imaginary. So it's equal to this, and beta is equal to omega square root of LC. This follows from this equation. Now, how do we compute these parameters, this inductance per unit length and other parameters? So now, so far this L was just a theoretical concept that if there is a transmission line, there could be some inductance per unit length. Now, but how do we compute it? One way to do that is we can take help of this relation that we just discussed. So then from here we get L is equal to mu epsilon over C, which is equal to, say, where this mu r and epsilon r are the relative permeability and relative permittivity. So this becomes equal to mu r. Okay, this mu 0 and epsilon 0 combine to form c square, where small c is the speed of light, and this c upon epsilon r becomes c0. So c0 is the capacitance per unit length with air as dielectric. Okay, and so then this becomes equal to 1 upon c square multiplied by c0 square, because this happens because the permeability is usually equal to 1, the relative permeability. Now in practice, of course, you can find out the inductance per unit length uh, directly from some CAD tools. There are many CAD tools available which can directly give you there are many electromagnetic tools which can directly give you the capacitance per the inductance per unit length. The next important topic is about the loss. So when we, once again, if we consider the equation for the propagation constant, that is like this. So this is the real part, and this represents the losses in the transmission line, and this is the lossless, or I shouldn't say loss, yeah, lossless propagation constant. Okay, losses. So what are the various types of losses in a transmission line? So alpha could be a conductive. So these are the losses, like the ohmic loss in a conductor. Uh, it could be the losses in dielectric. So the component of alpha that accounts for the conductive losses, let me call that alpha C. Then losses in dielectric, I call that alpha D. And finally, so this is the final one is radiative. Now for this course, we shall assume that the losses are only either conductive or the dielectric losses. But still, how will we find out these values of these of the various losses? So to find, first of all, conductive losses happen in the, if we consider again the differential element, differential length of a transmission line. So this R accounts for the conductive losses. Actually, I should have written it like this, only the R, not the L. And this G accounts for the dielectric losses. Okay. So how to find out the values of this alpha C and alpha D? So we are assuming alpha R is equal to 0. The total value, the final value of alpha that we will get will be the combination of alpha D and alpha C. Okay. Okay. So to find out alpha D, what we do is, let's consider this gamma. So gamma is given by J beta, which is given like this. Now let us assume that this beta is replaced by beta tilde, which accounts for the losses. Okay. So so in order to do that, let's go back to our Maxwell's equation. So let us start with this equation. This is one of our Maxwell's equation. Here J can be written as sigma E. This is Ohm's law. And D is equal to epsilon E. So if we have sinusoidal time dependence, recall that this equation can be simplified like this. And then from these two equations, we can write this equation like this. Now, this expression, if I take j omega out, then I will get something like this. Let me call this quantity as epsilon tilde. So then this gamma, coming back to this expression that I was trying to use. So here I have written gamma is equal to j beta. This is for lossless. Let me try, and this beta is given by this expression. But now our epsilon has changed to epsilon tilde. Okay. So let me do one thing. Let me see what happens if I substitute in place of this epsilon, epsilon tilde. So my beta, my lossless beta is given like this. My beta tilde, which now accounts for loss, or which is the complementary, or I should say, which is the complementary expression using epsilon tilde. So this becomes equal to omega mu epsilon minus j sigma upon omega. Fine. Now if I take omega mu epsilon common, then what do I get? I get 1 minus j sigma upon omega epsilon, and this raised to, now if I expand this one binomially, what I get? So what did I get then finally? This is the expression for beta tilde, and gamma will be equal to j gamma tilde. So this accounts for the losses. Okay. Now this quantity is the same as our beta, normal beta, that is a beta without tilde. So I can write this expression as where this tan delta, which is known as the dielectric loss tangent, is given as so the now let me write the complete expression for gamma. I should not use tilde here because gamma itself. So gamma, which accounts for both loss as well as the propagation constant, is equal to alpha d plus j beta. Here we are just trying to find out the value of alpha d is now equal to half beta tan delta plus j omega mu epsilon. This becomes equal to, so this is the real part, this is our alpha d, and this is our old beta. Now, why is it that this only represents alpha d and not alpha c? That might be a question. The reason is that here, this entire derivation which we have done, so here when we started with these Maxwell's laws, the losses, look here, we have considered this j term, right? Now, where does this j apply? J is when we are considering the current density due to the variation in the magnetic field. Now that is purely within the dielectric, okay? So that's why this entire loss expression for alpha d, that for alpha that we derived, is entirely for the current density that appears in the dielectric, isn't it? Because see here J is given by sigma E. Okay. Now the say when we are considering a transmission line, the losses due to variation of electricity, or the since this J is dependent on the electric field, so this J represents that current which occurs due to the electric field present between the two conductors of the transmission line. In other words, it represents this leakage current that happens between the two conductors. And which element accounts for that leakage current? It is the element G. Okay. So we were discussing the derivation of alpha D, this one. In this lecture, we shall discuss the derivation of alpha C. So as I had mentioned, alpha C arises purely due to the conductive losses. So in a transmission line, where are the conductive losses occurring? So if we go back to our differential element of a transmission line, so I have this R delta Z or delta Z. Okay, so this part, this shunt conductance, is where the dielectric losses are occurring, right? And we saw that why in the previous derivation, why the J, the current density, represented only the dielectric losses, because this J was created due to variation of electric field between the two conductors. So this J is purely the leakage current between the two conductors, and that is why the entire derivation that we did here is because of accounts for the dielectric losses. Now, for conductive losses, you might say that one simple way would be to measure the overall resistance. Just measure the series resistance throughout the transmission line, and that should give us the total losses, right? Total value of R, and from there we should be able to compute the value of the conductive loss. The problem is it's not so easy. One reason why it is not so easy, because this R that we measure at DC will be different at microwave frequencies. And why is that? Why is the value of R different at DC as compared to microwave? The reason is that the skin effect. We saw how the skin effect changes the effective resistance offered by waveguide at higher frequencies. It increases the effective resistance, and so because of the skin effect, R measured at DC will be different from that measured at microwave frequencies. And so the losses that you compute cannot be you cannot use the DC resistance to compute the total conductive losses. Instead, one relation that is of help to us is this one, that we see that one relation to the power that is being transmitted at a particular distance Z from the source is given by this expression. Now, this comes from electromagnetic theory. Those of you who have taken 301, you must have come across this expression. So here alpha C is the real part of the propagation constant and accounting only for the conductive losses. So from this we can get a relation alpha C is equal to minus 1 upon 2 Pz dP upon dz. Okay, so this is a simple relation that we can use to compute the alpha C. Here this dP upon dz represents power loss per unit length. Okay, and Pz is the value of the it is the value of the power at a particular distance Z from the source. So this now you might say that Pz will change, right, with different value of Z. Yes, it will change, but so will the value of dP upon dz. So this is more appropriately, this relation is given by minus 1 upon 2 Pz dP upon dz at z. Okay, at that particular value of z. Now, one example, I am using the second edition of POSAR. So in example 2.7, chapter 3 gives a sample calculation of this alpha C. One other way of finding out the total power, the value of alpha C, I beg your pardon, is to use something called Wheeler incremental rule. Now you can see example 2.8 in POSAR. Okay, they what this Wheeler incremental rule is that they try to find out the alpha c in terms of the geometrical parameters of the waveguide. So, for example, for a coaxial waveguide, let me try to refresh. Okay, so for a coaxial waveguide,